Hello, everyone. Nice to have you here. We are really delighted to have this new webinar with you. I am Mathieu Marmion from Specim, and I'm not alone this time. I'm really happy to be with my colleague Rainer. Rainer, please introduce yourself.
Hello, my name is Bärs. I'm from Specim. I'm an application engineer specialist here. Nice to meet you all.
Thank you. Thank you, Rainer. So we are both here for you for this webinar about SisuROCK and its enhanced version. You will see there will be a presentation which is about 41 minutes, sorry. And during this presentation, we actually have two guest speakers as well. You will see there is Phil Harris as a Chief Technical Officer from Terracore. And there is also Juhani Ojala as a Chief Geoscientist from Geopool. So please look at the recording. Also, during the recording, you will see there will be some polls, some questions, and we would be really glad if you could answer those. Also, if you have any question to ask after this recording, please type them in the chatter, and then me and Rainer would be really delighted to answer all of them. I will try to take the easy one, and Rainer will get the hard ones, right?
Thank you, Matthew.
Anyway, so please, if you have any question, just write it in the chatter. We are back in about 41, 42 minutes. So have a good show, have a good webinar. See you soon.
Yeah, see you.
Specim has been founded in 1995 as a spin-off of VTT, the Finnish National Research Centers. Since that day, since 1995 until today, we have delivered more than 11,000 devices, hyperspectral devices all around the world. That means spectrograph, but also spectral cameras, hyperspectral systems in general. Nowadays, we're at about 90 employees, and we are located all around the world. Our headquarters is in Oulu, Finland, but we also have facilities in the United States, in Spain, in Germany, and also in China. We also have a network of distributors all around the world, and they would be really happy to contact you or to be contacted to speak about the SisuROCK. Since 2020, we are part of Konica Minolta, and that's really great. It has been like this, improving our vision and also our perception all around the world. But that's enough about Specim. Now let's speak about SisuROCK, and I will join Rainer to speak with us. Here we are in the Specim production facilities, and behind us here we can see the SisuROCK, behind me and Rainer. So Rainer, can you tell us more about this SisuROCK that is behind us?
SisuROCK is a nice instrument. It has multiple cameras, modular. You can pick and choose which cameras you want, all of them or just one of them. It's fully digital. It provides digital data, so you scan once and then you can analyze the data to answer different questions depending on your needs. You don't have to revisit the core box.
Is it a new product?
No, this is actually not a new product. We have added some new camera options there. We have the new thermal camera coming up, the FX120. We have just added a 3D imager there, giving a topographic image of the full core box, and some other minor improvements.
How many cameras can you put in there?
In this configuration, current configuration, which we have sold many units of, we have a maximum of 4 cameras now. One is the 3D imager, and then we have 2 cameras using halogen lights and one using the thermal illumination. We have an option in the future, or we have plans to build an extended version for 6 cameras.
So you mentioned that we can put hyperspectral camera, but not only.
Yes, correct. We can also put a very high resolution RGB camera, providing a photographic-like image of the core, which geologists naturally want. Then we have the 3D imager, which gives us the topographic.
Okay, so we have high resolution RGB,
yes,
3D imager, and hyperspectral cameras.
Several hyperspectral cameras.
So you can put several. Can
yes.
you tell us why would you choose one camera versus another one?
Well, different minerals respond in different wavelength ranges. The standard camera I would say, is the shortwave infrared from 1000 to 2500 nanometers. It will give you the main alteration minerals and many other important minerals. But for the quartz, for example, and feldspars, you will need the thermal camera from 8 to 12 microns approximately.
Okay, so SWIR, let's say that's the bone. So
Yeah.
that's the one
Yes.
which is giving you the most common
Yes,
information.
yes, yes.
When you want to go for quartz and feldspars, then you go for the FX120,
Yes.
which is between 8 and 12 micrometers.
Yes.
What about between 400,000 nanometers?
Well, in the VNIR range, you have the rare earth elements which are responsive, which are of course now very important in the current electrical battery production industry.
So depending on your need, on the mineralogy that you are looking at, you
Yes.
can choose the right camera. So it's very like a versatile solution,
Yes,
basically. You
it
can
is.
custom it as you want.
It is, yes.
Okay. And then you can add as well those cameras which are not hyperspectral, but which can bring you some information
Yes.
as well.
Sure.
Can you acquire all the data in one go? Can you explain us
Yes.
a bit the workflow?
It's a nice instrument. Behind me we see the camera's illumination, and under them is the scanning table. You put the core tray on the scanning table, and in a single scan it will acquire data from all the cameras, including the white and dark references, which will ensure that the data is correct.
So the white reference tile is already included
Yes.
in the platform. It's
Yes.
already there.
It's there, it's included there, and it will be scanned every time.
So basically, one scan, and for each camera which are connected to their own
Yes.
computer, you can record the data.
Yes, it will be stored on its own computer. There is a computer for each camera and in its own folder.
You touch one point which is important, it is the illumination, because we spoke about the camera themselves, and everyone knows that in the world of hyperspectral imaging, illumination is crucial.
Yes,
Can you tell us about the illumination here?
we are using a double-sided illumination for all cameras except for the 3D imager, which is a laser-based instrument. The double-sided illumination will give you minimal shadowing of the core, which is important.
Okay, so now we understand how you
Yeah.
can optimize like this quick acquisition as well, because it's double-sided illumination. How fast does it take to make a measurement?
This is a fast instrument. This is typical time from loading a core box to loading the next core box is around 2 minutes.
2 minutes.
2 minutes, yeah. That means that in an 8-hour shift you can scan 150, 200 boxes. The problem is no longer the speed of the instrument. The problem is the logistics, feeding the scanner with
Yes.
enough boxes and transporting them there.
So basically you put the box on the sample tray,
Yes.
and then in one go you take the data for all the camera, and this is done in about 2 minutes.
Yes, correct. And
That's
everything is stored. You have the core box number, start and end depth, project name, and everything else is stored in the metadata with the files.
How big the box can be?
The box maximum size is about 65 centimeters times 150, and maximum weight is about 50.
By the way, can you measure only boxes with the SisuROCK, or you can put some rocks?
No, you can put mineral samples, powdered samples, rocks, everything. The height of the table is adjustable, so you get the top of the samples always in the focus region, which is very nice.
For the focus, how do you do the focus here? How do you adjust it?
The focus is done, like in cameras, by hand by rotating the forelens, but the camera is then looking at the focus grids, which are built into the scanning table. And on the screen you can see the spatial profile across it, which you then optimize to give the best possible focus, the sharpest.
So you have the white reference which is included,
Yes.
the dark reference is done with a shutter which is
Yes.
in the camera,
Yes.
and then you also have the possibility to adjust the focus like this.
Yes.
You mentioned you can adjust the height of the camera
That too.
as well.
Yeah, that too. Because you have core boxes, core trays of different widths. You want to capture more or less the whole box. So with narrow boxes you can bring the cameras down and avoid capturing on the sides, and you get a better spatial resolution then.
Then yes, you can
Yeah.
get better spatial resolution as well.
Yes.
Okay. Anything else you would like to point out about this instrument, this platform?
we have sold many of these and they have worked very well. We have, I think one of the oldest one is more than 10 years old and it's still in active use, very tough use. So they have turned out to be very robust.
Okay. Yeah. Thank you.
Yeah,
welcome. Thank you for all those explanations.
Hello, everybody. My name is Phil Harris. I'm the Chief Technical Officer at Terracore. Terracore is a company that has been dealing with geological drill core imaging solutions for a fairly long period of time. And one of our partners has been Specim, and we have a series of SisuROCK systems in our fleet. I'd like to talk. I'm going to basically talk a little bit about those today and how we've used them and what we can do for geology, how their use is for geology. So just a quick introduction to Terracore. We're a hyperspectral core imaging solutions company. We provide customizable hyperspectral solutions and services. These can range from acquisition and processing services through to system rentals, processing solutions, and then into system sales, leasing options with associated support as well. So we're really trying to get core imaging out into the geological marketplace. So why is hyperspectral imaging important for geology? Well, first of all, it captures an image of the drill core. And as you can see from the image on the screen, it captures all the textures in the rock and the associations of the different veins or alteration on the rock. It's a rapid, non-destructive measurement. So you can do it over large periods, large volumes of data, but also do it without losing your sample as well. There's a low sample preparation requirement, but obviously if you have sand or dirt or anything on the core, such as this tape, for example, then you will lose any information about it because it is a surface technique. However, it is an analytical measurement, so it means that we can start to compare between different boreholes and start to correlate across a project basis. Also, very importantly, the way that we've applied it here using the SisuROCK systems is that it's an on-site measurement. These systems can be taken to site, and as you can see from this drill core storage area in Australia, there's a very large volume of core that one might want to be moving for imaging. So clearly you need to move the system rather than the core to the location. So it provides a comprehensive mapping and coverage with a combination of the mineralogical information from the infrared and the textual information from the imagery, providing you really with that true geology. It's got a high information content and which is really lends itself towards artificial intelligence and machine learning, and it is a reusable data set. It's like geology. You can come back to it once you've got a different feel for your rocks and start to ask different questions from the same data set to be able to reveal some of the answers. So our journey for core imaging really started for me in early 2000s. With Specim, we did our first VNIR shortwave trial at their facility in Oulu in Finland to actually demonstrate the concept, and this was done with a mining company in South Africa. We later on in the 2000s, we imaged using a long-wave infrared uncooled system, and we did that trial. We know how important long-wave infrared is for geology, and I'll explain that shortly, but that was certainly our first venture into the long-wave. Then our first campaign or system that we got out there was in early 2009, where we took a SWIR, single camera system, to South America and imaged 15,000 meters of core. And that was what's currently being termed the proto-Sisu, because it was the early version before the SisuROCK systems. Obviously, that work led to demonstrating the value of the imaging data, and also demonstrated the need for these types of platforms. The first SisuROCK, in the Gen 1, we were involved in early 2012, and we also had one of those systems built into our fleet. It was a 2-camera system, either an RGB SWIR or a VNIR SWIR combination. Then in 2014, we were fortunate enough to get access to the long-wave infrared OWL camera from Specim, and that's there was the primary long-wave camera until the FX120 has been developed. And we trialed that in 2014, and that proved very successful and demonstrated very significantly the value of the long-wave infrared for the imaging of drill core. So later in 2015, we had the first installation and campaign associated with the SisuROCK system, which is a Gen 2 system, and it had 3-camera system, basically RGB, the VNIR shortwave infrared, which were combined at the time, and a long-wave infrared camera. And that undertook over 200 kilometers of core on a specific project. In early 2019, we did some trial work on the mid-wave infrared camera from Specim, the FX50, to have a look at what its value would be for geology. Now, the mid-wave infrared is a really interesting range. It doesn't, there's not a lot of information about it, the main focus has really been the shortwave infrared and expansion into the long wave. But the mid-wave infrared still has value, and we were able to trial it, and it gave us enough information to be able to make a decision that it was worth integrating these into core imaging platforms. So and combined with that, later on in 2019, we worked with the 3D imaging system. And that's really interesting because it gets the topography of the core. And we were really looking at trying to look at the core condition as well, and having that as an additional component that one could add to the core imaging data set. The first integration that we had was with the mid-wave infrared camera onto a SisuROCK platform was in early 2022, and that is now in operation. And then finally, in this year, we have got a 3D imaging system integrated into one of our fleet systems, and we're currently using it on our operations at this point in time. So that hopefully gives you an idea of how we've engaged and the importance and our involvement, Terracore, and our partnership with Specim in terms of, first of all, developing and trialing that application, but also then implementing and rolling it out into the market. So for geology, there are certain things that cause changes in the spectral response. These are related to electronic and vibrational processes. And these charge transfers or stretching or bending vibrations create absorption features or australan peaks that allow us to identify different minerals. These occur in different wavelength positions, different regions of the infrared, and they allow us to, one, identify minerals, but also by looking at some of those features and monitoring those shifts of those features, we can start to look at chemical changes inside those specific species of minerals. So you can see a chloride compositional changes, for example, and then also we can start to look at crystallinity effects. So the changes and the impact on the shapes and the occurrence of these features allow us to look at the crystallinity of your illites or your white micas, and even into your chlorinites. So there's a lot of information that the infrared can give you through these absorption features to be able to help you identify the species and the changing nature of those species within inside your samples. If we look at the region of the infrared and we go from the ultraviolet, the UV, into the VNIR, which is the visible near infrared, into the shortwave infrared, midwave infrared, up into the long-wave infrared and the very long-wave infrared, the regions that we're currently the minerals that we're seeing within those regions and where we see responses in the spectral signatures. In terms of the visible near infrared, we start to see transition metals, so we can see different metals within inside some of the different minerals. Iron oxides are responsive there, as well as very importantly the rare earth elements. As you move into the shortwave infrared and up into the midwave infrared, we start to see the hydroxyls, and these are clays and phyllosilicates. You see water responses, carbonate, hydrated sulfates, and other OH-bearing minerals, such as the amphibars. And this is a very important range to identify alteration and some of the alteration minerals that we see. Then as we move into the regions further up in the midwave and into the long-wave infrared, we start to see responses related to the silica oxygen, aluminium oxygen, and silica. And those are giving us are silicate minerals, you know, the typical rock-forming minerals, the quartzes, the feldspars, the pyroxenes, the garnets, etc. And that's what makes the long-wave infrared a very important region. It is often referred to as the thermal infrared, but we've gone with the long-wave infrared just to fit in with the same nomenclature of these other regions. So those are the regions that we see, and also these are the cameras that Specim is using that actually show you the full coverage across these regions with these different cameras. So we put together a table which just sort of gives you just a guideline to what sort of minerals one might be able to see and what regions would be important to be able to look at it. So you've got it across from the visible and the infrared, shortwave infrared into the midwave and up into the longwave infrared. If we look at the phyllosilicates, we see that the shortwave infrared is really, really good. Longwave infrared is not bad. You do get a lot of interference from other minerals, so it becomes a little bit difficult when you have different coexisting minerals. We're a little bit uncertain as to what we can do in the midwave at this point in time because we haven't had yet enough practical experience with that region. But then importantly, when you get into something like the tectosilicates, you see that those are really being detected well in the long-wave infrared. There's a possibility of some of these things in the mid-wave infrared, but not very much detectability in the short-wave infrared. So you can't look at the spectral signature and actually identify these minerals. Then you have regions like the carbonates, where you start to see carbonates in the short-wave infrared, in the long-wave infrared, but also very significantly in the mid-wave infrared. And the mid-wave infrared is very good for the carbonates. And then finally, just to have a look at some of the other areas, hydrocarbons are really good in the mid-wave. That's where we're seeing the hydrocarbons, the CH4s, but we can also see it in some of the other ranges. Oxides, iron oxides are very good in the VNIR. But then the oxides and sulfides, because we're not having absorption features in the ranges we're covering, it's very difficult to see them. But we do with the signatures map an effect related to the sulfides and the oxides, and therefore then we can map these groups out, but not necessarily speciate them. So I've just looked at a couple of examples of some of the instruments inside our Terracore fleet. We have these the SisuROCK Gen 1, which is the early SisuROCK systems. We have mobile systems with the Specim cameras on board, which are much more portable, easy to move around. And then we have the more robust and more the multi-camera SisuROCK system, the Gen 2 system itself, which is typically where all of our long-wave cameras are being implemented on. So I have just a couple of examples of images generated from the cameras. The RGB image really creates a very nice high-resolution image with the 8K cameras, as you've heard about. You can get down to 50 micron pixel size for the camera, and you image a full core tray. Moving into the shortwave infrared, you can see we're in the sub-millimeter, but up to 1.5 millimeters. Same for the shortwave infrared. And then with the new FX series cameras, FX50 and FX120, you can see you can get down, in some instances, get down below 1 millimeter, sub-millimeter spatial resolution of the data. And then additionally, quite excitingly, you start to add the 3D profiling system, the 3D imaging system, and that is really allowing us to map core condition. So you can start to look at whether you've got rubble, broken core, round core, cut core, but then you can start to look at the breaks, which allow you to get things like the rock quality definition, the RQD, and then combining these fractures with the mineralogical information from the other infrared cameras. We're looking at starting to get the fracture surface textures and also the mineralogy around those fractures, and that can start leading to your rock mass rating. We can also start looking at breaks versus breccias versus broken core, differentiating those so we don't get confused between those, and then also start to look at improving extraction of the information from other data sets as well. So it has an integral component, and I think this is a really nice camera that rounds off the core imaging application. You're really covering most of the regions of the infrared, so you can use them in different combinations if you want, but then also adding this gives you that geotechnical component, which is often obtained from Terracore as well. So just to look at examples, I know we talk about this being really rapid. I think just quickly, these are a couple of projects, and I just want to highlight the mean acquisition rates per day, and then you just need to look at the shift hours because we're really talking about an 8 to 12 hour shift generally. But we know that because you're imaging individual boxes, and you would have seen that from the videos, that you're imaging that all at the same time. So it depends how many boxes you can feed, and that's around about 200 boxes a day. And then depending on how many channels you have in that, then it certainly can influence the meters. But obviously, we don't count as geology, we don't count boxes, we count meters. So it gives you an idea of what you can do. So it really depends on how easily you can feed the core. On some of the smaller projects, we've achieved 500 meters a day. But in some of the larger projects, 55 kilometers of core, we've done over 2,000 kilometers in that period as an average per day. And then in these 200 kilometer cores, we've done just under 1,500 meters per day. It really has depended on how well prepared the samples are for it, and how well smoothly the operation is set up, and then the number of channels within inside the core tray itself. So you can see these volumes and get an idea of it. And it really is, these are true application examples. So obviously with the data set, you can produce, first of all, the images, so you can actually see what's happening. You can relate it to the geology and see how you log it, and you can actually begin to log on the drill core itself. So you can start to put those boundaries where you see it in the core. And alongside that, you can start creating these lithological logs. And alongside it, you can put all sorts of different data sets, these machine learning data sets, the mineralogical variations and some of the spectral variations, which allow you to pick those changes. And you can start to then use these in a multi-data set approach to be able to generate, or at least accurately determine the logging parameters. Also, from a mineralogical perspective, I've got an example of the skarn deposit, where we're looking in the long-wave infrared, and we're looking at these amphiboles. You can see the two signatures, the one from the actual core itself and the other from the library, so you can see how similar they are. This is a garnet signature, the andradite. It's a quartz signature that you see within it, and then this is the diopside, the clinopyroxene signatures that you have in there. And these can map them out, and you can start to see the paragenetic sequences of these minerals and the alterations associated with this specific deposit. So in conclusion, really, this drill core imaging can be used across the mining life cycle, all the way from exploration, when you're doing lithology and structural definition, defining alteration and alteration patterns, and being able to adjust your drilling program to be able to explore more for more of your ore. Resource definition, so you can start looking at geological modeling, resource domaining, so you can start including that and look at your resource extension. Into feasibility, where you can use it for resource geometallurgy, your ore and waste characterization, and also for geotechnical work. Then finally into production, where you can look at it from a grade control perspective, or production-based geochemistry, and then other material observations that you might find during the production operations. So I hope that that's given you a good indication of what you can do with the core imaging data sets, and really is for us really about this digital transformation and the ability to bring the rock to the cloud. So thank you very much.
Hi, my name is Juhani Ojala. I'm the Chief Geoscientist at Geopool. I will be presenting hyperspectral scanning example from the Kittilä mine, which is currently the largest gold producer in Europe. Kittilä gold mine is a world-class deposit with almost 10 million ounces of gold in total. I had a little bit exposure to spectral geology in 1990s in Australia while doing my Ph.D. on a Granny Smith gold mine. And I met Tom Kadahi from SisuROCK. I came back to Finland in 2001, and I worked with Vikke Kuosmanen, and we followed with the great interest high-local development in Australia, and even made a proposal for Geological Survey of Finland to get one instrument. Time was not quite right, but Vikke pursued further and teamed up with Rainer Bärs and Specim to investigate using imaging hyperspectral camera to image drill core. They were looking for suitable core, and at the GDK with Helena Hulke, we found a good example of gold-related alteration zone from Petäjäselkä, Kittilä, Finland. After Vikke showed the scanning results and classification as shown on this slide, it was clear to me that this is a brilliant way to map alteration in drill core. And best thing, that the imagery was a real measurement and not a human estimate. Map of the central Lapland, showing the location of the Kittilä mine. In addition, I added the gold deposit of the Finland as a reference, just indicating that there's a number of other gold deposits around. There has been a couple of operating mines, gold mines, Saattopaara and Pahtavaara. And here is a little bit more detailed look at in the SWIR deposit, showing the open pits, and it's also showing the complexity when you start getting in a mine scale. You start to see a number of different lithologies also between these two mafic packages, and the cross section on the right sort of shows that the mineralization is subvertical. Here is a detailed picture on the drill core, what the ore looks like. It's quite, how to say, uninteresting looking. But then when you look at it in more detail, you can see that the distal alteration consisted of calcite, alpite, chlorite, rutile, and proximal alteration is sort of alpite, muscovite, dolomite, or anchorite. And there's also additional quartz and, of course, arsenopyrite and pyrite. And one peculiar thing about the Kittilä mine is that in the SWIR deposit, that there's a lot of amorphous carbon in this deformation zone. And when looking more in a detail, even more detail, sort of in places the ore is sort of bleached and has a sort of quite strong few percent disseminated arsenopyrite, very fine grain though. And in places it is very strongly sheared and brecciated, and amorphous carbon calling on the fractures. And when looking the gold, where the gold is situated, even more detail, gold is within the arsenopyrite and pyrite, and even there it is not evenly distributed, but it's in growth zones. And from petrographical studies, people have noticed that actually the sort of second generation pyrite and arsenopyrite is the main host. And when you look in this alteration pattern, it is pretty similar to what has been mapped in a greased fascist orogenic gold deposit worldwide. Only exception is a little bit that the alpite alteration is pretty much going through the whole ore zone in SWIR. And this slide is here to show the location of the drill core, how it goes through. So it's drilled at about 500 meters below the surface, and going through the ore zone pretty much straight angle. And also it indicates that the ore intercept consists of several lenses, and on the western side the rock is pretty much undeformed and well preserved. And then we have the ore zone, which is strongly deformed, proximal alteration, and then we're going through it and we're getting to distal alteration, which in the eastern side is basically goes all the way to the end of the holes. Set up at GDK 2018, and once you get your palette and rock movements set up very well and all the metadata is ready, scanning 200 boxes a day wasn't any problem. And that happens in a normal 8-hour working day. And once you get things scanned, after about a week, Terracore have depth registered the images and started processing, and you start getting results back. And once you get both shortwave infrared and long-wave infrared, you get quite a number of products from both wavelength ranges. And you get data which you can show this as images or as a strip logs. In the beginning, it feels like there's almost like too much data. But the one thing is that when you're stacking up this data, you start seeing that these different wavelengths and the variation in different wavelengths, they definitely form zones. And this GeoZone product is trying to capture it in a sort of one column, the main changes. A lot of changes you can also see from the dominant mineral maps. To strip logs and summary plots, you can of course look at the data in a more detail, zooming in a different scales and start looking the products compared to your RGB or human vision. But then real value of the data really comes when you add the assay data and the geological logs and start sort of looking the data in a context what human has seen or other assays, and data start to explain back and forth. And in the Kittilä mine case, it was quite clear first, what I noticed was that the aspectral pixels increase in the ore zone. And this is obviously due to increase in graphite and sulfides. Oh. And then other thing when I started to sort of looking different parameters and also sort of split the dominant mineral maps into individual minerals, that really sort of this proximal zone was marked very well with white mica. And interestingly, white mica increases, and it sort of forms a little bit like a rabbit ears to the data. And then when going to the other end is the disappearance of epidot, and this is the classic especially in the basaltic rocks, that when gold-related alteration, that epidot is pretty much first mineral disappear. It's probably not easy to see, but then the chloride a little bit increases, again marking a little bit like rabbit ears for the mineral zone. And then when you get into the ore zone itself, quartz a little bit increases, and this same column here is also a little bit probably better visualized by the long wave false color image, where the wavelength shown as RGB image are such that your quartz is shown as red color. And so this ore zone really sort of, or mineral zone is popping up. And then in Suurikuusikko, alpide alteration was supposed to sort of, and in a feeling when you visually log the core, you see that it sort of get albedoized. But then I guess it's more question about that other minerals disappear, some of the dark minerals disappear, and rock looks a little bit different, paler maybe. But well and truly, there are zones which are strongly albedoized. And the other thing which is in line with the classic orogenic gold alteration, that even though we have carbonate alteration is pretty much detected in a full core length in both holes, but when you're coming to this proximal zone, your carbonate increases. And also when you're looking a little bit over the wavelength, so this 2200 wavelength, many places it sort of correlates with the code alteration, and it seems to be a little bit doing that same thing in SWIR as well, and the depth of the same sort of showing the increase of the white mica and the wavelength change. And this is probably a little bit better again looked in as an image, and you sort of see this wavelength change of the 2200 range around the ozone. And also the when Terracore provided the carbonate composition index, it also sort of this ozone seems to be sort of popping up, forming its own zone. So the carbonate composition also changes, and this was already a long time noticed in SWIR that once you change from calcite to sort of more anchoritic or sideritic compositions, that's where you start getting the elevated gold values, and it has been long used there as a guide that when you start putting the rocks into the assay. So this discovery that we have different ore types with slightly varying mineralogy and the correlation to the hardness pretty much immediately sort of came to my mind that there's certainly useful data also for the mining engineers and for metallurgists, that how the rock and different ore types will behave in milling and grinding and other processing. So it's not only geologists who benefit from this data. And I think I'll end there. And as a last image, I'll leave you, Rainer and Vikke Kuosmanen, looking the core, and for last memory, you can see the colorful images what they were able to create about 2007 when SisuROCK story started. Thank you very much.
If you need anything which is related to SisuROCK, if you need to have some data, if you need to measure some samples, if you need a quote, or if you need to have a demo, please do not hesitate to contact us. You can see here, you can contact us at info@specim.com or on our website, specim.com. We will be happy to come back to you. Now we are ready to go to the Q&A. So it's nice to be back here with you, and we are ready to answer your questions. So remember, if you have more questions, you can still type them in the Q&A, in the chat, and then they will be transferred to the questions. So me and Rainer, we will do our best to answer everything. So Rainer, are you ready?
Yes, I'm ready. Thank you, Phil, and thank you, Juhani. That was an interesting presentation.
That was indeed. So let's start with the first question. Please comment on the nature of core trace. So Rainer, do you want to comment here on the nature of the core?
I see that Zarin has several questions regarding these, more about the material of the core trace. The size of the core tray doesn't matter. The SisuROCK will take any size of core tray. I think that we have noticed that plastic core trays in some cases can give a reflection from the plastic and the plastic signature on the core sometimes. So maybe wooden core trays or metal core trays are to be preferred, but there is no big difference as far as I know.
Okay, thank you, Rainer. Then I can take the next one. So is SisuROCK or can install in SisuROCK 3 hyperspectral camera without the 3D camera? Yeah, if you're not interested in having the 3D camera, indeed you can have like 3 hyperspectral camera. In the standard version, you can have like 2 halogen-based cameras. So you can have an FX10, you can have an FX17, you can have a SWIR camera, 2 of those, and then you can add as well a thermal camera, which is FX50 or the FX120. If you have the extended version of this SisuROCK, which is slightly longer, then you can have 3 halogen-based cameras, so it means RGB, FX10, SWIR, FX17, or then the FX120 and the FX50 at the same time. But yeah, you don't have to have the 3D sensor. The next question, you mentioned 3D or RGB camera in SisuROCK. Is it from a third party with its own software? So Rainer, do you want to handle that one?
Yep, it's they are third-party cameras. Specim doesn't manufacture or design 3D or RGB cameras, but it's all integrated into Specim software. We call it Lumo, the software. They are all controlled through Specim software in a single way. It's all integrated.
So yes, so as you say, so it's a third-party supplier, but the software for you, it doesn't make any difference, basically. That's good. Then another question. I am more interested in applying your camera for healthcare imaging. All right, so here it was more dedicated for geological application, but we'll answer. Having said that, once I remember we had a customer who has been laying down, you remember, Rainer, on the SisuROCK table, and it has been measured completely. It was like for different type of application, but once we had this. If you think about healthcare application, in fact, our cameras, our hyperspectral camera can be used for this type of application as well. So if you think about tumor detection, for example, like for skin inspection, I invite you to look at our webinar about VNIR spectral range, because this spectral range is actually better for this type of application. If I think about healthcare as well, you could think we had some application about the color of the teeth with like fake teeth. So you want to be sure that you don't put a yellow teeth at the middle of a white one if you need to have a prosthesis. So there was this type of application as well. Some other one could be like in a surgery block, and if you want to inspect while you are making the surgery, if the tumor has been completely removed. Here again, it was an application which could be tackled with our camera. But anyway, so here, for more like medical-oriented application, I invite you to drop an email to info@specim.com, and then we will come back to you. Is it possible to add more camera to SisuROCK later on? Later, for example, like we start with the SWIR camera, and then we add, if we want to add FX50 or FX120. Rainer, I think this question for you.
Yes, absolutely. That's a very good question. It's very interesting for a lot of people. The full SisuROCK concept is very modular. You get the frame, and then you pick the camera modules which you want to include with the frame. And later, if you want to expand, you just add another module, another camera. So you could start with the shortwave infrared camera, and then later, when you need it, add a long wave or an RGB module to it, or a 3D camera. You can expand it later, absolutely. It's very flexible.
Thank you, Rainer. Is SisuROCK can inspect and find the gold mineral and how much it contains? Which wavelength is suitable? So I must say this is a question which is asked quite often. Can you find gold, for example, in core and things like this? Well, I'm not a geologist myself, but Rainer, tell me if I'm wrong. I understand that you don't find the gold as such, but you need to find the minerals which are surrounded or allocated somehow to where the gold could be found.
Exactly. And Juhani's presentation, which we just saw, was a perfect example on how to locate the gold, because you are looking at all the minerals surrounding the gold zone. And so no, not gold, but the minerals.
But do you know exactly, maybe not all the minerals, but which spectral range will be better for the gold associated mineral? Would you go more like for SWIR, or do you know that, or it depends?
It depends. My feeling is that the shortwave is the basic tool, which will give you a lot of things, but there is great value in the long wave here
as well. Okay. Is Terracore providing training to companies to utilize it? What costs are involved? The cost, we cannot answer that. If you have, I mean, everything related to to financial matter, we cannot answer on this webinar because, as you can imagine, we have as well our competitor who is watching, so we don't want to give this kind of hint. But about the training, this we can answer. And actually, Rainer could maybe answer better than I.
Yes, Terracore provides services to its customers, including trainings. I would invite you to contact Terracore for these questions. Terracore provides a full packet of services of hyperspectral. So ask them.
Okay. Can the 3D camera measure the 3D model of the sample, and what is the format of the measured data? So basically, the 3D camera is here to indeed measure like different shape of your sample, if it has some cracks, if it has some volume, and things like this. Regarding the format, I think it's an NV format,
Yes,
if I recall
yes,
well. Yes.
Yes, it's a 2-band grayscale NV image with the height for each pixel encoded as the grayscale.
Are SisuROCK deployed at core yard, or is it a lab-based instrument? Well, you saw from the video the size of the system. So basically, the way it is made, it is more dedicated to be in a room, like to be in like a core logging storage facilities or something like this. To have it on a yard, it's more tricky because it's not weatherproof. So it means like if it is raining, if it is windy, if it is dusty a lot, and so on. So it's not made for that. So it is an instrument which is more made to be like in a lab or something like this. It is correct. Here that was Harry telling about the VNIR webinar, and then we go on. Does SisuROCK come with ready-to-use library or model of rocks recognition as Phil presented, or rather should customer train own rock samples? Rainer, do you want to answer or shall I?
We can both use. Please start.
Well, okay, I start. Well, first of all, SisuROCK, it's a measurement instrument. So here you use it to acquire data about your rock. What you're asking, it's more about data analysis. And then for data analysis, there are several options. You could use a software which has been presented by Juhani or also by Phil, but also you could use another one. So for instance, if you want to open the data, you could use NV. And because the data, they are saved in an NV format. And NV already includes some library, like the one of USGS, but there are some other ones, where you can actually check, compare our data, the data obtained, with the SisuROCK, with the USGS library. You can do that. We also have our Insight software for data analysis, and soon there will be the possibility to build your own hyperspectral library. Notice that you can do that as well in NV, but with our software, there will be this possibility in the coming weeks, I would say. And also you can open an existing library like the one from USGS. So as such, we do not provide really a Specim library, but you have possibility to import or to compare our data with existing library. Rainer, do you want to complete?
Yes, one thing which you should consider is that in a research environment, you might measure 5 boxes or 10 boxes or 50 boxes, and you have time to process them by a manual system where you process each box individually. If you have an operational system like Phil showed here, which scans 200 boxes a day for several days in a row, you need to have a dedicated system, a batch processing system for that. And that's a tailored system then, which we don't provide. Specim does not provide.
Rainer, then the next question. What is the time span between data capture, the scanning, and delivery of the process interpretation output? Is there any way to get the process information in real time right after scanning? Do you want to handle that one?
That's a very good question, very interesting question. As Phil said, or I think Juhani said, that the normal time span between scanning and between Terracore delivering data is maybe 1 week. That's the magnitude of the. But I know that Terracore and others are working on faster processing and analysis of the data, not maybe full processing, but getting the first results very quickly.
But I guess it depends on the amount of data you want to process as well. I mean, like if you have only
Yeah.
one box, it's much faster than if you will scan like hundreds of meters.
Yeah, well, the key is starting the processing soon enough, not after the processing. So you have to continuously process. But I think we are getting there, getting the data almost immediately after scanning.
Then there was a question about real time. Maybe it relates to mining industry. So here I would like to highlight that our SWIR camera is not compatible with the Specim one yet, but still there are some other one. And Specim one, it is a platform which could be used for real-time data analysis. And for example, depending on the minerals you are looking at, FX50, FX10, FX17, they are compatible with the Specim one, which could be suitable for real-time data analysis, which might be useful as well for mining industry. How can we get ideas about focal lengths of cameras to adjust one into another? Well, here I would say the easiest is to contact us because we know exactly which lens are available for which camera, which ones can be used at which minimum measurement distance, working distance, what will be the field of view, what will be the pixel size, what will be the depth of field. So here I would say you contact us and here we can choose the lens for you, which is matching basically with your requirements. Can the system return mineral percentage per depth interval from 2?
I think,
please. Yep.
yeah, that's a very good question also. And the answer, of course, this is more in line with Terracore's capabilities, but the answer is yes. You can calculate the relative amount of minerals. It's a pseudo-quantitative amount of measurement because it's not a real assay. But yes, you can output your data in that format.
By the way, I would like to highlight that we have Juhani who is here online and he has been answering to Jukka. So Juhani is already also answering here.
Good.
So good. So if our participants they start to have discussion together, that's wonderful. I love that. Then for detecting the rare earth element minerals, which VNIR camera is the best in terms of spectral spatial resolution and sensitivity? For the rare earth element, indeed, this is mostly VNIR, and here we have the FX10. So in terms of spatial resolution, it has 1024 spatial pixels. The good thing is that we have several optics available. So you can have either a wide field of view, but also you can have a very narrow one. And we are now soon releasing a new lens, which will allow basically user to have a pixel size, which is about 10 micron. So you can make really high spatial resolution or high resolution analysis. So FX10 is the one we would recommend. And in terms of sensitivity, this is good as well. The good thing here is like you are using the system in a lab environment, so you can put a lot of light. You don't have the real-time constraints that you will have the sample moving at 2 or 3 meters per second. So here the sensitivity is not an issue. So that was Jukka now answering, Juhani answering to Jukka. For detecting the rare earth, that was a question I just answered. Any plans to add other analytical equipment onto the frame, such as Raman, X-ray fluorescence, to complement the hyperspectral data? So here, as you saw, we already have the high resolution RGB image, a 3D sensor. Heiner, do you know if there is way to implement other like type of sensors?
That is also a good question. We have discussed that a lot, and we get these questions a lot that we should integrate all kinds of sensors into the SisuROCK. Theoretically, it's possible. We could do that if we wanted to, but there are some disadvantages. For example, the fact that the SisuROCK is a very fast instrument. We scan 2 minutes per box, while most of the others, like XRF, are much slower. They would slow the system down. So, in my personal opinion, it would be more sense to have separate instruments for the XRF and the hyperspectral. But I know that these combinations have been made, and We are looking at that, but at this time we don't have any actual plan on doing that.
Thank you. Could you comment more on conducting conducting hyperspectral imaging of ore interval more than non-ore or waste part, and can that help to save time for analysis, or is it recommended to check whole drill hole core? I have to read it again, I have to say. Could you comment on conducting the hyperspectral imaging of ore interval more than non-ore or waste part?
I can reply to that.
Please go ahead.
Yes, we recommend that you measure the whole drill hole, because if you measure only the ore part, it's like, to use an analogy I've heard from Phil, it's like looking at the candle flame with the magnifying glass. You're not seeing the whole picture. You need to understand what's going on with the geology there, and have something outside the ore zone also. So it's recommended to have enough material to give the full picture.
And actually, we also see that Juhani answered are proved to be like more complex than I expected, so you can see more details and visually. Then we had someone asking if the solution can differentiate from salt, different type of carbonate, different type of minerals. And basically, Phil was explaining that if you have like diagnostic absorption feature, like if those can be separated from each other, so then yes, this technology could be used for that. He highlighted especially that, for example, for the carbonate, it works really well. For the salt, still some work needs to be done. Maybe Rainer, you know something a bit more about the salt, or?
No, I think Phil replied pretty well there. That what did he write? That some have signatures that can be distinguished, but there is not extensive experience about those yet. But yes, some can be identified.
And then there was a question about X-ray. Do you want to say something like about X-ray diffraction?
Yeah, well, Phil answered that too. XRD can be used to calibrate the hyperspectral data to confirm the identification of minerals in hyperspectral using XRD. But they basically identify the same things. XRD is maybe, to my understanding, more specific.
Okay. Then the same person, we have someone who's asking a lot of questions about fracture analysis.
That's a good question. I know we are working on that with the 3D imager. I'm sure Phil would have a very good view on this also. We are coming there. Fracture analysis, QRD calculations and things like that. I think they are coming because we have the data now in the 3D imager in SisuROCK.
True, with the 3D imager, actually the data, they are saved in the NV format. And with the 3D imager like this, you have the possibility to see the different type of cracks that you can have actually in the rocks. So yes, this is a great improvement, a great addition basically to the hyperspectral data.
Yeah, but I think the algorithms are coming. They are being developed as we speak to be automated.
Okay. So now we have another question. We are particularly interested in clays. Do you think that analyzing only very fine ores in sample could provide the identification of clay? So do you mean if you want to measure powders? In my understanding, so clay could be measured. I think the shortwave infrared is actually the best camera for that. Can you confirm here?
I'm not sure I understand that question. Measuring very fine ores in samples. Clays can generally, I believe, be identified in the short wave. but I'm not sure I understand the meaning of this question.
But in my understanding, it is asking more like if it is like powders or if it is like big rocks or it could be like core. That's a little that's a bit the way I understand it. But okay, so maybe if you have a question, like you can send us an email at info@spekim.fi and then we can .com, sorry, and then we can come back to you after that.
Yeah, absolutely. We'll be happy to reply or discuss more about these questions.
Is this technology applicable to oil and gas exploration? Yes, we have actually customers here who have been like buying our SisuROCK like this with different camera, especially for that. I mean, like you can have drill core in boxes, and then this could be interpreted with a hyperspectral imaging data with a hyperspectral camera.
Yes, I think it's applicable both in normal oil exploration when you want to look at the layers or the geology in the deposit, over the deposit, and also in oil sands. This is applicable.
Do we have anyone else who would like to ask another question?
I think we explained everything so well, or Phil and Juhani explained everything so well.
Oh, we were so confusing that no one knows what to ask. That could be the second approach. Ah, we have someone. I have a question regarding the spectral calibration with the Spectral. Is it calculated for each scan box, or we can use the value from the first scan for the rest? So now you have to understand actually what it is for. Here's the spectral clone. When you measure the white reference, it means that you measure the incoming light seen by the camera. So if the sensitivity of the camera does not change, sometimes it can with the temperature, or if the illumination doesn't change, then it's fine. You don't need to have the white reference acquired every time. But in order to be sure of this consistency, because you may have small variation in the dark current of the camera, and also you may have small variation in the illumination, then you can also acquire the white reference every time. If you think about online application, for example, when you have a conveyor belt and then you cannot stop to take the white reference and the dark and so on, so you need to take into account to make the hypothesis that everything is stable, illumination and also dark current of the camera. Then you need to make some condition for that. You need to be sure that your illumination is stable. You need to put the camera sometime in a temperature stabilized casing. I think especially about the thermal cameras. But here in the sense of the SisuROCK, so you don't have to take it every time, but since you can, why not?
Yeah, I would make a note that the spectral on the white reference isn't used for spectral calibration. It's used for intensity calibration. So spectral calibration is a different thing.
This is a different thing. You're right. Have you tried to apply this technology over a moving conveyor belt with different particle size? Yes, actually, this type of technology, our hyperspectral camera, are used a lot for industrial application over conveyor belt in the food industry, in the recycling industry. So it could be in the mining industry as well. So yes, so this time you don't need to have a translation stage. Like here you have a sample tray, but you could have a conveyor belt which is moving at 1, 2, 3, 4, 5 meters per second, depending on the resolution you want to have. Why are your cameras so big in comparison to the CMOS-based cameras that are based on Sony IMX and such? Okay, so here it depends what you want to compare with. So if you think about just a camera, a CMOS camera, a CMOS camera, it's only a chip and the electronic which is around, and sometimes you have a little bit of cooling. In our case, we have to add some optical part like spectrograph and things like this. So the spectrograph includes some lenses, it includes some gratings, a lot of optical component, and it takes some space. So if you compare the size of our camera, by the way, with the one of the competition, we are not that big at the end of the day. But this is true if you compare with what you could think of a GoPro, for example, you could put on a helmet. No, this is not the same, but this is not the same technology either. Rainer, what is the next question?
It's very exciting to see how far core scanning has come since the early work at Chevron. That work, I had the good fortune to work on that on the early. I'm now retired. Okay, that's Bill talking. I recognize Bill's name. It's a question. Hi, Bill. And there's one from Philippe.
You provided clear information.
Yeah.
Our group looks forward to working with SisuROCK as soon as we obtain the necessary resource. Good. Please, we will be happy to help you to work. And actually, when we get a SisuROCK, we have a team of person who is able to come to install it. And actually, Rainer is part of the team to come to install it, to help you, to teach you how to use it. So yes, happy to help.
Absolutely.
Someone else? It seems that we run out of questions, so I think we got already quite a few, so that's good. So again, I would like to thank everyone for attending this webinar to look at it. I really would like to thanks a lot. I will answer to that one, but I will still thanks a lot Phil and Juhani.
There's a new.
And there is a new question. You know, it was the same. Always when you say
Yep.
it is the end, plop, you get a new one. That's perfect. I should do that more often. What are the recommended QA/QC procedure to ensure that the scans are well paid for?
Do you want me to reply?
You can, or I can. It's up to you.
Yeah, please do.
Okay, so we have a QA/QC procedure with our SisuROCK, which actually monitor when you take the dark reference, is the shutter well closed, or if you take the white reference, is also you have, you know, like the whole illumination, which is actually like with bulbs which are burned or not, or if you have like homogeneous, or if you're actually looking at the white reference, if you're not looking at something else. What else? It tells us well if we have drop frame. So meaning like if you acquire data, if some of them have been taken away. And by the way, when we are dealing with the world of hyperspectral imaging, it's important to have 2 hard disks per computer, so one for the operating system and one dedicated to the data to avoid to have drop frame like this. So here are the things coming to my mind. Do you think about something else for the QA/QC, Rainer?
Yeah, I think one good QA/QC standard operating procedure is every day or twice a day to measure a standard sample palette with standard samples, so you can monitor the spectral calibration that it's not shifting. You can't use it for spectral calibration, but you can check that it's not shifting, and maybe you can trace it later. So have a standard target with the known targets.
Yeah, it's always good.
Yeah.
Okay, so thank you everyone again. So thank you Rainer, thank you Phil, thank you Juhani, thank you everyone for being here. I don't know exactly when we are going up, how long it takes to build, install, and deliver to client. Well, to deliver, it depends on the cameras that you are taking. So it depends on the camera. So if you take, for example, FX10, FX17, it is faster than if you will take a SWIR on FX50 or on FX120. It depends on that. Typically, the delivery time, it could be from weeks to few months. It really depends on the camera you plan to have. For the installation, Rainer, I think once we have everything built and shipped, I think it's a question of 1 week, isn't it?
Yeah, the typical installation when we come to the customer site is about 1 week to install and train. Yeah, but the delivery time of cameras can be short or long, but there is also the delivery time of the SisuROCK frame, which has been quite long. We are talking of about several weeks.
Then we have another question. Let's go on. So how much extra value for long wave infrared if we have SWIR and VNIR for mineral mapping? Well, we know that some minerals, they have really good diagnostic spectral feature in VNIR, SWIR, but some other one in long wave infrared and only in long wave infrared. There are some minerals, I think about feldspar and also quartz, you need to have the long wave infrared to be able to identify them. So basically, it brings some value. It just depends on your application if you need to identify those, yes or no, but it has some value.
Yes, there is a table of mineral identification versus the wavelength range, both on our website and on Terracore website. It's Terracore's table. So please look at that and see which minerals can be typically identified in which wavelength range. That would give you an idea of the value. It depends on your problem.
Why some SWIR and VNIR signal has zigzag signal? It's like saw teeth along the spectral range between 1000 and 2500 nanometers. It could be an issue, for example, with the referencing, for example, with the normalization, if the right formula is used, or if the dark reference or if the white reference is taken as it should be. So
Well,
that
yeah.
could be.
For this, we should really see the spectra of the data
Yeah.
before saying anything.
Yeah, it's hard to say just as a, yeah.
It could be the
many
mineral.
things. It could be many things as well.
Yeah.
I don't dare to say bye-bye anymore because we get more questions actually. So still wait a bit. Yes. No, it is from raw count anyway hard to show. Yeah, well, you can send us some data cube and then we can have a look here. Just like this in the webinar, it's a bit hard to just say if there is an issue or if there is no issue, or yeah, it's a bit difficult. But please contact us, send a data cube, we can have a look.
Okay. Thank you, Matthew, and thank you, Phil and Juhani, for your contributions, and Phil for his answers.
Thank you, everyone. Now we quit. So again, I don't know exactly when the next webinar is going to happen. Anyway, you are welcome to join again. Remember, info@specim.com or specim.com for the web address. So I wish you to have a nice day, evening, night, morning, wherever you are. Everyone, bye-bye.
Bye-bye. Have a good day.